so we're going to talk a bit about modern physics now, and we're going to start off by taking a close look at something that you're probably at least partially familiar with. Now, these days most people have a Blu-ray player, and one of the reasons that the technology exists is it actually uses, you load in your little disc, your Blu-ray disc, and then inside the Blu-ray player it will actually shine a laser at it, and then a detector will pick up and read the data from either the reflected laser beam or, yeah, it should actually be the reflected laser beam, so I should draw my detector back up here. And there are little notches in the Blu-ray such that sometimes the light bounces off and goes up into the detector, sometimes it bounces off and gets reflected somewhere else. So that gives them ones or zeros. If it sees the light, that's a 1. If it doesn't see the light, that's a 0, at least conceivably. And that's how it gets binary. Now, the reason the Blu-ray players can hold so much more data than the similar technology that used the same approach, in the past with CDs, they actually used infrared lasers or infrared diodes, and DVD players actually used the red lasers, much like the red laser pointers that we're used to. Now, in the late 90s, we developed a blue LED, one that is made out of, if I'm not mistaken, indium, or I'm sorry, no, not indium. I think there's a little bit of indium in there, but it's primarily gallium nitride, which is a semiconductor. All right, so that's extra information. But the important thing is, based on the energy levels of this semiconductor, this gallium nitride, in fact, it'll look a lot similar to some of the other problems that we'll take a look at, though we'll look at different energy levels. But thanks to the energy levels, where the electrons can be inside this material, gallium nitride, it actually has a tendency of giving off light at a very specific wavelength. For our case, for the Blu-ray player, the wavelength should be right at about 405 nanometers. Now, based around that, so we can learn a little bit more about the Blu-ray players themselves, I've got a couple of questions. So the first thing I want to know is, what is my frequency of this light at 405 nanometers? Okay, we'll define that. We had the relationship in class, and this is related to wave equations, where our velocity equals our frequency times our wavelength. In this case, we're talking about light, so that is going to be equal to c, the speed of light. 3.0 times 10 to the 8 meters per second. All right, well, I know my wavelength. It is 405 nanometers, but like all of our other equations, we want to use SI units. So this is nothing more than 4.05 times 10 to the negative 9th meters. Or I'm sorry, not negative 9, negative 7. Negative 7. For nanometers, I'll take this, 405, and I'm going to multiply it by 10 to the negative 9, because this is what nano means, and that'll give me 4.05 times 10 to the negative 7. I apologize for the slip up there, but never hurts to write it out, as you can see. So we have 4.05 times 10 to the negative 7. That is my wavelength, my lambda, so I'm going to plug that in here. I know my speed, which is the speed of light, and so I'll end up with my frequency equals 3.08, or I'm sorry, 3.0 times 10 to the 8th meters per second divided by my wavelength, which was 4.05 times 10 to the negative 7 meters. We can see that the meters cancel out, and we're left with 1 over seconds. When we evaluate this, we come up with about 7.41 times 10 to the 14th hertz, where hertz is equal to 1 over seconds. We can see that we have 1 over seconds here, also known as inverse seconds. All right, so that's our frequency, but I'm not done there. I want to find out the energy that each one of these photons, the little beams of light, at this frequency has. Okay, so the equation that we had in class was that our energy is equal to Planck's constant times our frequency. So I'm going to take Planck's constant, which in the regular units we use is 6.63 times 10 to the negative 34th joule times seconds. And I'm going to do frequency, which is, we just found 7.41 times 10 to the 14th hertz, which is 1 over seconds. Our 1 over seconds, which is a hertz, cancels out with the seconds, and we're left with joules, which is our unit of energy, which is good, because that's what we're looking for. So my energy is going to be equal to, running through those numbers in joules, I get 4.91 times 10 to the negative 19th joules. I can also use my conversion, because one of the energy units that we've been using when we're dealing with very tiny energies is the electron volt. I can convert this energy, 4.91 times 10 to the negative 19th joules. 1 joule is equal to 1.6. Oh wait, no, I've got that reversed. Sorry. That's why it's always nice to draw them out. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. Okay? And I multiply these out, and I'll find that in electron volts, which you'll see why we use them when dealing with this, it comes out to 3.07 electron volts. This is one of the reasons why when we're dealing with these energy scales, electron volt becomes a much more common unit. Now, as I've mentioned in some of the classes before, and I'll go ahead and point it out here, I told you during electricity and magnetism that energy, our potential energy, was equal to a voltage times our charge. Well, the electron volt is actually very, very descriptive. You'll see that the conversion factor is actually the charge of the electron. And so if I take this and I multiply instead, where I imagine E is nothing more than the charge of the electron, and I multiply this in, it will actually give me the value in joules. So that's where we get an electron volt from. Okay, but this is the energy. You could also find it in electron volts by using, instead of 6.63 times 10 to the negative 34th joule seconds, there's also a version of Planck's constant where it is in electron volt seconds, but it's not one that I prefer to use. So, now the final thing that I'd like to know is we found that light actually has momentum, despite the fact that it has no mass, and that's related to, among other things, Compton scattering. We found that when light has interactions with electrons, for some reason we still have conservation of momentum, and that from that we end up with the light itself has to have some form of momentum. The equation that we got in class was P equals h divided by lambda, though the more standard physics approach is P equals h bar k, but I'm going to keep things simple. So, I want to find out the momentum of the light. Well, I can plug in Planck's constant, which is 6.63 times 10 to the negative 34th joule seconds, divided by my wavelength, which was 4.05 times 10 to the negative 7th meters. And when I evaluate all this, I plug all of that through, I find out that the momentum that I have is equal to 1.64 times 10 to the negative 27th kilogram meter per second. That is an incredibly tiny amount of momentum, but that's just for one photon. It turns out if you've got a lot of photons, it can begin to add up. Now, this equation is one that we will use in some of the other problems as well. We'll find that any solid object, any particle, can also be, we can use this relationship to find out what its equivalent wavelength is when it's acting like a wave.